Hello, this video lesson is on infrared spectroscopy, and that's a technique that is used to identify molecules and work out the structure of molecules. And this instrument that we have on the right is an infrared spectroscope, and it can produce spectra, which are graphs that can be used to describe the shape of a molecule. So what this lesson encompasses is the absorption of the infrared by the bonds, which is what leads to the spectrum. We're going to have a look at lots of different versions of infrared spectra and see how they're generated. Then there's something called the fingerprint region, which is individual to a particular molecule, and on a database there's each molecule's fingerprint, which is the infrared spectrum for that molecule. And lastly, we're going to see how all this impacts global warming. That's what this lesson is about. Let's start off with absorption by bonds. So what happens in a molecule is that the bonds have energy, and they vibrate and they rotate. And here we've got a water molecule, the red being the oxygen and the white dots being the hydrogens. And as you can see from this diagram, the bonds can stretch and then they can stretch back, and that takes energy. And then they can also vibrate this way and back that way. And they can also rotate, as you can see in these curly diagrams. They're rotating around. And that movement, whether it be vibrating or rotating, takes energy. And the particular frequency of energy that is needed to rotate most covalent bonds lies in the infrared part of the electromagnetic spectrum. So here's an electromagnetic spectrum, just as a little reminder, and we've got the low energy waves at the right hand side here, and gradually as you go from right to left you're going to get higher energy. In the middle there's the infrared section, and right up at the other end are the X-rays and gamma rays, which are the highest frequency, highest energy, shortest wavelength electromagnetic rays. Okay, so it just happens that when we're talking about vibrating and rotating bonds, covalent bonds, then the energy that resonates for those covalent bonds happens to lie in the infrared part of the spectrum. So let's look at that in a little bit more detail here. So we've expanded the infrared part of the spectrum, and what you can see is down. This is the low energy, and this is the high energy. And you might know from your physics that energy equals h, which is Planck's constant, times f, which is frequency. And so energy is proportional to frequency, given that h is a constant. So at the right hand side, this is low energy and it's low frequency as well. And this is high energy and this is high frequency. Now, as it happens, when we look at infrared spectra, we use a measure called wave number, and wave number is proportional to, so let's just write this down here, wave number, and it's sort of like wavelength. In fact, it's the reciprocal of wavelength. It's proportional to frequency. It's proportional to frequency, and as you can see, this scale here is in fact frequency. This scale here is frequency, so we've got low frequency on the right and high frequency on the left. But we actually want to use a measure called wave number instead of frequency, and it's just to make the numbers a bit easier. So when we got down at this end of the spectrum, the wave number is about 500, and the units are centimeters to the -1. Reciprocal of centimeters. And when we get up to the high energy part of the the infrared part of the spectrum, the wave number is about 4,000. Okay, and again we've got centimeters to the -1 being the unit of wave number. Now, the reason I'm saying that is because each of the bonds that are in molecules they absorb the infrared radiation at slightly different energies. So if you were to shine broad spectrum infrared onto a molecule, most of it would go through, but the frequencies that, or the wave numbers that resonate with the particular bonds in that molecule get absorbed and don't get passed through. Okay, so what I'm going to do now is I'm going to suggest that at this end we've got carbon-carbon bonds and carbon-oxygen bonds. And then slightly higher energy, we've got double bonds, for example, carbon-carbon double bonds, carbon-carbon double bonds, and also carbon-oxygen double bonds. And triple bonds are in the middle, so you might have a carbon-carbon triple bond in the alkynes, or as in the nitriles, you've got carbon-nitrogen triple bond. And then we've got single bonds up at the high wave number part of the spectrum. So carbon-hydrogen, oxygen-hydrogen, and nitrogen-hydrogen. So they're typical bonds that you find in organic molecules, and each of them absorbs different frequencies or wave numbers of infrared radiation. And we can use that to identify the molecule. Okay, so which is what we're going to have a look at on the next slide. So we've got a machine. Here it is, and that's going to generate a broad spectrum of infrared. It's going to shine it on a sample. So we shine lots of all the different infrared wave numbers through this sample, and depending on the bonds that are in that sample, some of that radiation is going to get absorbed, and those frequencies that are not resonating with the particular bonds in that sample will pass through. And so from that, this machine will detect what comes through and then draw a graph from it. And the graph sort of looks like this. And unclearly, you can see here, this is transmittance. Okay, so and this is 100 at the top and 0 at the bottom. So if you're shining the infrared radiation on a molecule, most of it's passing through. But at a particular wave number, here's the wave number along the x-axis, at a particular wave number, take this one for example, that clearly resonates with a bond that's in the molecule of the sample, and so that has not passed through. So you can see most of, if you track along here, most of that radiation has been absorbed by the molecule and none of it has got through to the detector. Same here, we could say that this particular wave number of infrared has been absorbed by some bonds in the sample and has not gone through. Okay, and so what happens then is that this is a infrared spectrum for a particular molecule. All right, and the shape that it is unique to that molecule. And what we can do is we can have a look at these spectras and identify the functional groups and the bonds, and eventually work out a displayed formula for a particular molecule. So what scientists have done over the years is that they've worked out all of the wave numbers that are absorbed by the different bonds in organic molecules. All right, so you get a table such as this. Okay, so we've got all the bonds on the left-hand column there, and we've got the wave numbers that are absorbed by those particular bonds. And it varies a little bit from molecule to molecule because it does depend on the adjacent bonds as well, and that's why there's a range there. So if you look at the two, well, they're called peaks, they're actually troughs, aren't they, but they're called peaks. If you look at the two peaks that I've pointed to with the blue arrows, one's at about 3000, so that could mean that we've got an OH bond of a carboxylic acid in there. notice here that OH bonds also appear at a different part of the table. An OH bond in an alcohol is going to absorb a different infrared wave number than an OH bond in a carboxylic acid, just because of the adjacent bonds that are to it. Okay, and if we look at our second peak, it's at about 1700, which might be this bond here might signify a carbonyl group on a molecule. Okay, and so what we might want to do now is just to have a look at what's called the fingerprint region. So at about 1500, at about a wavelength, wave number of about 1500, if we draw a dotted line up, it's supposed to be a straight dotted line, and between about 1500 and about 1000, that's called the fingerprint region, because in that range of wave numbers, you actually get a pattern that is unique to a molecule. So what you can do is you can store that pattern for a particular molecule in a computer, so that if you have an unknown molecule and you pass it through your infrared spectrometer, you get a spectrum like this, and then you can compare it to all the spectra that you have in your database, and that can be used to identify that unknown molecule, just as an unknown fingerprint can be compared to fingerprints that are in a database to identify the person who owns that fingerprint. Okay, and that's called the fingerprint region. Now what we might do is we might have to have a look at some more detail by means of some examples. So here, let's have a look at this spectrum. This is an infrared spectrum of ethanoic acid, and let's look at the various troughs. Okay, so we've got a trough here, this broad trough on the left-hand side there, and that can be said to be an OH bond in a carboxylic acid. One, because of the breadth, identifies it as an OH bond in a carboxylic acid, and two, because of the particular wave number that it occurs at, of about 3000. So that's going to give you a clue as to what the molecule is. We already know that it's ethanoic acid, so it's going to have that OH bond. So we've worked out that that bond there. What we'd also expect, if it was a carboxylic acid, would be some double bond to the oxygen. If we referred back to our table of wave numbers for that carbonyl bond that is in an acid, you would see that it comes at about 1700 wave number, and so that is further evidence that this is a carboxylic acid. So let's now have a look at a different acid. Here we've got butanoic acid, and you can see this broad pattern is quite similar to the one above, and also we've got a peak at about 1700 or 1800 there for the carbonyl group of the acid. So on this part of the spectrum for butanoic acid, it's very similar to the left-hand side of the spectrum for ethanoic acid. And so whilst the two spectra so far have helped us establish that they're for carboxylic acids, it's not identified the individual carboxylic acid. So for that, to do that, we need the fingerprint region, which, as I said, was between about 1500 and 1000. All right, so what I can do now is just superimpose those two charts on top of each other. Have a look at that here, and you can see on the left-hand side to the left of about 1500, they're very similar, aren't they? You've got the peaks at 1700 and 3000, and the charts overlap very closely. But to the right of 1500 in the fingerprint region, they're quite different, aren't they? And so that difference there would be what would identify the acids as one ethanoic acid, and the other one butanoic acid. So I hope that illustrates the fingerprint region in a little bit more detail for you. And we can move on to talk about global warming for a bit, and what the relevance is to infrared absorption. Okay, so let's think about the radiation that comes off the sun. The sun is very hot, and the radiation is of very high energy. All energies come off the sun, but on average it's very, very high energy. So that high energy radiation is not the wave number of radiation that is absorbed by the covalent bonds in molecules such as water vapor and carbon dioxide and methane and stuff. So that radiation passes straight through, and that's what's illustrated by this diagram here. So most of the sun's radiation passes straight through the atmosphere, which is made up of nitrogen and oxygen, a bit of carbon dioxide, water vapor and methane and stuff. So that radiation all passes through. A little bit of it reflects back into space. But most of it passes through, and then it hits the surface of the Earth and warms up the planet. And because the planet is therefore a warm object, it's going to emit its own radiation. But of course, the planet is not as warm as the sun, and so it doesn't emit as high energy radiation as the sun. So what comes off the Earth is lower energy, and a lot higher proportion of the energy that is emitted by the planet is infrared. And so that infrared radiation is emitted and goes up into the atmosphere, and a lot of it is of the wave number that is absorbed by molecules such as carbon dioxide and methane and water vapor. And when it does, those molecules absorb that infrared radiation and therefore heat up. And that heat becomes part of the temperature of the atmosphere, and then those molecules radiate their own heat back down onto the surface of the planet. So much less of the radiation that's coming off the planet actually escapes out to sun, out to space, and more of it is absorbed by the bonds in those molecules and is therefore absorbed, and the atmosphere is heated up, and those molecules emit their own infrared radiation and send it back to the planet. So there you have the connection to global warming. I thought what we'd do now is try some questions. So here we have a question that may well be an exam question or part of an exam question, and we're given a spectrum, and we're told it's a carboxylic acid. That's kind of them, and we're told the MR is 74. So then what we have to do, part A, is to identify the bonds that create the peaks marked A and B. So here's A, here's B, and you can see that the wave number of A is about 3000 and the wave number of B is about 1700. So what we need to do now is refer to our table, and in the exam you get a table on your data sheet of, and the table looks like this. So you've got the various bonds, and you've got where those bonds, what sort of molecules those bonds are in, and you've also got the wave number of those bonds, the wave number of the radiation that is absorbed by those bonds. So let's have a look at about 3000. So 3000 like this. So that is illustrating an OH bond in a carboxylic acid. And we were told it was a carboxylic acid, so we're quite confident in saying that that is the OH bond in the carboxylic acid. And let's have a look at B. B is about 1700. So 1700 is in this range here. It's a bit less than 1750, which is a carbon oxygen double bond, and it is a carbon oxygen double bond that might be in a carboxylic acid. So B might be the carbon oxygen double bond in the acid. So that's the answer to A, and B, we want to know to draw the displayed formula of the molecule. Okay, so we know it's a carboxylic acid. We know it's got a carbon oxygen double bond, and we know it's got a hydroxyl group on it. And the other thing we're going to refer back to is the MR being 74. Okay, so how much of the molecule have we accounted for so far? So carbon's 12, oxygen 16, we've got 2 oxygens, and we've got 1 hydrogen. So that all adds up to 32, 33, 43, 45. And we're going to subtract that from 74. So 74 take 45 equals 29. So we know the rest of the molecule has an MR of 29. So connected to that carbon has got to be a carbon hydrogen at least. So that's 14. All right. So that's a good chunk of the 29, and I think intuitively it's going to be like this. Let's just make sure. So this part of the molecule here, let's just circle it in a blue dot. We have to make sure that what we think is the rest of the molecule adds up to 29. So we've got 12 for the first carbon, 12 for the second carbon, and 1, 2, 3, 4, 5 hydrogens, and that's 24, 29. Okay, so there we have it. We're pretty confident that what we've drawn in red there is the displayed formula of the molecule, which is propanoic acid, as it happens. So there's a typical question that you might get in the exam about infrared spectrometry. What we can do is we can try another quick one. Here's another exam question. So we've got another spectrum here, and this just shows you an unknown molecule. Use the spectrum to identify one important bond that can be found in the molecule. Okay, and we don't even have to refer to the table, but I think we can probably remember this is about 1700, and so we can remember from the first question that we did that this will be a carbon-oxygen double bond in a carboxylic acid. So that's about it for this lesson. Let's just make sure we did all we wanted to do. We wanted to have a look at how infrared is absorbed by bonds, and we looked at the little diagram of rotating and vibrating bonds, and then how the machine shines broad spectrum radiation at a sample. Some of the wave numbers are absorbed, and from that we get the spectrum. And part of that spectrum is known as the fingerprint region, which is unique to a particular molecule, and they're all stored on a big database so that you can identify unknown molecules. And we've also seen how particular molecules, like methane and carbon dioxide and water vapor, absorb infrared, all right, and therefore trap some of the radiation that is shone by the Earth and absorbed by the Earth and stops it getting back out to space. And that was global warming, but they're good, so I hope that's been clear for you.